Is it better now? Good. So let me use this one. Yeah. Oh. This is not the system. I use the tool. Full screen. No. Yeah. It will take some seconds, but then it will show up, hopefully. No, it succeeded. In it opened. No, it's okay. I will take the fourth. Hopefully, I will leave time and floor for questions. So why it's not? Ah, okay. No, I needed to. Why it's not showing the first page now? No, okay. Okay, so ladies and gentlemen, welcome to my talk. And first of all, let me say that I'm glad to be here and participate in this academic celebration dedicated to the memory of Leo Apostel. And I'm also glad to have the opportunity to illustrate one of the research topics we are currently working on within the group on quantum structures at CLEA. As you know, so the activity, the research of the group of quantum structures is mainly related to the, let's say, identification of quantum structures across disciplinary boundaries. Okay, so in particular in cognitive domains. When I say cognitive, I in particular mean conceptual and linguistic domains. Of course, the idea is to get some feedback into the foundations of quantum mechanics meant as a theory describing physical systems or physical entities. Okay, so this is the main idea, and one of the topics we are currently working on concerns the identification of Bose-Einstein statistics in linguistic domains, and let's see how. Let me also say that I personally was trained as a physicist. Okay, now in Italy I'm considered, where I am employed, I am considered the philosopher of science, but I mainly use a lot of mathematics, let's say this. Having said this, I also think that this research aligns with Apostel's legacy for what concerns transdisciplinarity and the integration of worldviews. Okay, now let's do a family portrait. So this is our group at CLEA. The leader is Diederik Arts. And then we have very good and talented early career researchers as Ionito, Lester, and Suzette, as well as, let's say, more senior researchers as Massimiliano and Thomas. For what in particular concerns me, let me tell you a few things about my personal experience with the Center Leo Apostel. So I joined CLEA as a postdoctoral researcher in 2011, so some years ago already. And since then, my collaboration with the CLEA group on quantum structures, and in particular with the Diederik Arts, has produced more than 70 publications. So I think that this means something for me personally, because it contributed to my personal and scientific growth. So the experience in CLEA has contributed to my personal and let's say scientific growth. But in the meanwhile, I've founded, let's say, a more specialized research center whose acronym is CQSCS. It's the acronym for the Center for Quantum, Social and Cognitive Science, that more specifically works on the application of quantum structures, as I said, across disciplinary boundaries. So it fits a research program that has been called, has already been named in this event today, quantum cognition. Okay, it's a flourishing research program, I have to say, also from a technological point of view. Just a caveat regarding what we do. So this is not quantum. We do not do research on quantum brain. Okay, it's not quantum brain. It's not quantum mind. We look for the most appropriate mathematical structures for the description of a series of empirical data. This is the idea. So this means that our research does not require the assumption about the existence of microscopic processes in the human brain. Okay, we don't need this assumption, so we don't make it, right? So we are talking about quantum structures, quantum mathematics, quantum-like phenomena, and so on. There are different ways to say the same thing. Okay, of course, we have underlying reasons for using these structures, which in particular in those areas where uncertainty is present, where contextuality is present, where there is a state dependence and so on, which make a quantum formalism more appropriate than a classical formalism to represent this phenomena. So if you Google CQSCS, you will find the webpage of my research center, which is currently based at Memorial University of Newfoundland in Canada. And so if you are interested, just have a look at what we do there. Okay, now I will start by something that is known to people who work on the foundations of quantum mechanics, because this has to do with the role of indistinguishability, of physical indistinguishability, on the statistical distribution of identical entities, identical physical entities. So I will start by resuming the state of the art of what concerns indistinguishability in physics. Okay, so when I say identical entities, I mean 2 photons, 2 electrons, and so on. So, in classical statistical mechanics, the behavior of a large number of identical entities, which are also supposed to be distinguishable, because you can label their trajectory, them through their trajectory, is governed by Maxwell Boltzmann statistics. The situation is drastically different in quantum mechanics, because according to what, let's say, Dix calls this interpretation as the received view of identical quantum entities, they are completely indistinguishable from a physical point of view. This complete indistinguishability is incorporated into postulates that are typically part of what modern manuals on quantum mechanics say about this. The first thing is the tensor product postulate. You know how to put together 2 physical entities in quantum mechanics. You use the tensor product Hilbert space. The second is the so-called symmetry exchange postulate. It's a very strong postulate because it states that the state vector of 2 identical entities, 2 photons, 2 electrons, and so on, has to be either symmetric or anti-symmetric with respect to the exchange of any 2 entities. What is the result of these 2 postulates? Well, the result is that entities with semi-integer spin, like electrons, for example, must be in anti-symmetric states, and they have to obey a specific statistical distribution, which is a Fermi-Dirac distribution. This is well known, studied, and so on. On the contrary, entities with integer spin, like photons, like particles of light, must be in symmetric states, and they obey a completely different type of statistics, which is Bose-Einstein statistics. Okay, there are no other possibilities. This postulate, the symmetry exchange postulate, has an implication because it is responsible of the lack of statistical independence that characterizes identical quantum entities. I'll come back to this in a few slides. Because the requirement of symmetry or anti-symmetry mathematically forces the states of these entities to be entangled states. So automatically this breaks statistical independence. Now, coming to our recent research on this topic, well, we discovered the appearance of Bose-Einstein statistics in the distribution of the words contained in text of English language. A priori would have never said this. This is what we found, and I'll try to convince you why we found this empirical pattern. More, we explained this result so by making an assumption. The assumption is the following: meaning connects the concepts associated to the words of a text in a similar way as quantum coherence connects entities in physical domains. So what we, and this is the last thing we did, which is what I'm going to present, is to extend this study changing language. We did a study using Italian language for obvious reasons. Consider where I come from. Okay, so we found exactly the same pattern, the same empirical pattern. So let me now go back, and this is the theoretical part. I apologize in advance. There are some formulas. There is no Dirac notation. There is no notation in quantum mechanics, okay? But there are some formulas, at least, let's say, a formalization of what we did. So let us consider a text T made up of small n, different words, and the total number of words is capital N. Okay, so you have a text, you have different words, they sum up to n capital letter. N small letter are the different words, of course, because one word may appear in a text more than once, right? Then we order these words according to their decreasing number of appearance in the text. So you count. There are softwares who do this job. The words that appear in the text, you order them according to the decreasing number of appearance. Okay. So W0 is the most frequent word. W1 is the second most frequent, and so on till the last word. We have n small letter in small n in total. Now, and this is the first novelty of this approach, we attribute to each word an energy level. It's not physics. I'm not talking about physics, okay? It's a label. It's something we attach to the word, okay? Of course, we are trying to push the analogy with physics as much as we can, but we don't have to interpret this as a physical concept. And you see that this is the energy that depends on the frequency of appearance of the word in the text. Okay, so the most frequent word is given energy E0, which for this convention is equal to 0. You can make other choices, but putting the lowest energy equal to 0 is something that physicists used to do frequently. Okay, then we have the second most frequent word as an energy level E1 equal to 1, and so on. Okay, right. Now, if we denote by NEI, this thing, this, no light. Ah, yeah. NEI is the number of times that the word WI appears in the text. This we can recover from the text. Okay, we can count it. But then if we sum all these NEIs, of course, we have to recover the total number of words. Okay, but this number is constant in a text. The second, the second novelty that we introduce is, this goes back to our approach on words and concepts. Each word is associated with a conceptual entity, with a concept. Okay? Here again, in analogy with physics, we called the cogniton, no? Because in physics you have the boson, the photon, and so on. We called it the cogniton, but again, it's just a label to denote these words. The important thing is that these words are associated with concepts, and concepts are, in our approach, entities that can be in a given state and whose state can change under the influence of a context. This is the new thing of our approach. Then we call them cogniton. It's fine. But this is the new thing. This is different from our approaches to concept theory. A concept is not a set of objects in our approach. This is important. Okay, it's not a set of instantiations. Okay, so it is an entity in a state which we call a microstate, like in physics. They call them microstates. They are single entity states. Now, if we take a word, Wi, it has a defined energy. Okay, we have defined its energy, putting it equal to I. But since for each word Wi, there are NEI items of that word, NEI exemplars in the text of that word, the energy of that word is this product. Okay. Also, this is very intuitive. Okay. Now, the words, the different items of the same word are identical each other. Okay, because these are different examples of the same word appearing in different places in the text. Pay attention. If we consider two different words, they of course are non-identical. This can be conceptually distinguished if the words are different, right? It's just to clarify the situation. Then the total energy of all the words contained in the text is obtained by summing across all the different words, the words that are non-identical, the energy of the single word. Now, if this text is a large size text, so that we can make a statistical analysis as significance in the text, we can interpret it, again pushing the analogy with physics, as an ideal gas of cognitons, in which these two numbers, N and E, are constant. Okay. $1 million question. Which distribution shall we expect for the numbers of appearance NEI? These are the number of times that the word Wi appears in the text. A priori, one would say and we don't know, actually, first, a priori. But also, it may change from a text to another. No? Well, but there is a point here, very important, and has to do with the indistinguishability. And here we make the connections with physics. Because if you take the same word in a text, history, for example, that appears in different places in the text, and you exchange the two places, the meaning of the text does not change. Right? So you have a kind of indistinguishability which very closely resembles the type of indistinguishability you have in physics. Because you have in physics a symmetry exchange when you exchange the position of two photons. It's what quantum mechanics tells you, right? So this is a hint. But well, let's see what that comes from statistical analysis. So let's put there some formulas. Because in classical statistical mechanics, if you treat classical entities as distinguishable, the only statistics that you get is Maxwell Boltzmann statistics, and as this form of a decaying exponential, right? This is very standard, okay? In addition, you have that two different microstates are statistically independent. So the probability that two distinguishable entities are in a given microstate is just the product that each entity is in that microstate. This means statistical independence, right? So the probabilities do factorize. In quantum statistical mechanics, so I came back to physics, because of complete indistinguishability of identical quantum entities, you have two completely different statistical distributions. Because either you have a Fermi-Dirac distribution or you have a Bose-Einstein distribution. Okay, they are completely different. But in both cases, you lose statistical independence for different reasons. Why? Because, wait. Let me come just to the last line of this slide, then I'll consider the two parameters. You lose statistical independence for identical physical entities because in the case of fermions, you have a Pauli principle. Two entities cannot occupy the same state, so you lose statistical independence. If you have two bosons, for example, two photons, equally you lose statistical independence, but for different reasons, because photons tend to cluster together in the same state. I don't know whether you have heard about Bose-Einstein condensation, which is the extreme situation of this clustering together of photons of bosons in the same state. Coming to language, we don't find the Fermi-Dirac statistics in language. Okay, it seems that it appears in memory structures, but not in language structures. But Bose-Einstein statistics appears in language, as I'm going to show you in a moment. Coming back to physics, just to say that the parameters that of these formulas, you see in these formulas, there are some parameters, no? Right? That you need to fit by imposing suitable constraints, right? These parameters can be easily found. You see, this is B, the parameter B is the heat energy. It depends on the temperature. The higher the temperature, the higher parameter B. While A is this exponential, and mu in this formula is called chemical potential. It's not important at this stage, okay? Just for the sake of completeness. There is also this parameter F that is called the fugacity. Okay, so what we did. If you have a given text, you choose a given text from a given language, you have these two numbers, and E. You just count the words of the text and you get and E. Okay? So you also have the empirical numbers of appearance. Then what you do? You try to find the pairs of the parameters C and D and A and B, which tells you whether a Maxwell Boltzmann distribution, classical behavior, distinguishable entities, or a Bose-Einstein distribution fit the data. Okay? So you compare the empirical distribution, NEI, with the theoretical distribution given from a classical situation or from a purely quantum situation, and see what comes out. Okay? Well, what we found with the text of English language was the following. We found that in all cases we analyzed, Bose-Einstein distribution provides a good model for the data. It fits the data in an incredibly well way. Okay? You can do a test of statistical significance, of course, while Maxwell Boltzmann statistics does not work at all. But in addition, we also found the same lack of statistical independence that is observed in the behavior of bosons. Finally, and we come to linguistics. In linguistics, there is a law that is called Zipf's law. Okay? That says that there is a relation on inverse proportionality between the number of times a given word appears in the text and its ranking in the text. Okay? It is considered as a purely empirical law. There are some approaches, but there is no unanimous acceptance in the community. Well, our approach in terms of a Bose-Einstein distribution provides a theoretical explanation for the appearance of Zipf's law. Okay? But I'm not going to talk about Zipf's law. Let me go to the empirical part of our study. Now, what we did, we selected a digital library. Okay, it was a publicly available library, this one, BBIT. But we used, instead of English language, we used Italian language this time. Okay, maybe you can recognize some famous Italian authors of 19th and 20th century, like Alessandro Manzoni, Italo Svevo, and so on. There are also some novels for teenagers like this one or this one. Anyway, this is what we found that was publicly available. Okay, we could not find Comedy of Dante, sorry for this. But anyway, this is the technical part. So for each of these texts, we counted the number of words, and Lester, who is here, Lester Beltran, did very carefully this and seriously this job, highly professionally. So the number of different words, the total number of words, the total energy, and the parameters that best fit Bose-Einstein and Maxwell Boltzmann distribution. Okay, we did homework. And what we found is that the Bose-Einstein distribution, also for Italian language, models incredibly well collected data, the data collected from Italian language. Maxwell-Boltzmann distribution, which would work by assuming distinguishability of words, does not provide a good model at all. Okay? So we confirmed the results obtained on English language, extending them, but I think we also did something else by considering Italian language. Because we think that there is an intrinsic language-independent cognitive dynamics which governs the formation and combination of the concepts corresponding to the words that appear in a text produced by human language. Okay? This is our hypothesis, that there is something that occurs at the level of meaning, okay, that is independent of the language that is used to express that meaning. Then we became curious about this result, and we did what physicists do. We added uncertainty. We added randomization, a random element. Because if you add a random element, you would expect that Maxwell-Boltzmann statistics occurs, right? Think to a gas, to a macroscopic gas, no, of molecules, of a classical gas. Okay, So the molecules of the gas classically distribute because of uncertainty, no? According to Maxwell Boltzmann statistics. So if we had a random element to a text, we shall expect Maxwell Boltzmann distribution to start to appear as a consequence of this randomization. But what is the meaning of randomization in, well, these are some graphs that show, okay, that we did well, okay, it's not so important to describe it now. The effect of randomization I will explain in a moment. First, I would like to tell you something that that is related to the lack of statistical independence that is observed in a text, in the words of a text. Consider two words. I took this Alessandro Manzoni's Del Romanzo Storico, whose English translation is on the historical novel, as an example. Take one of these words, romanzo. Okay, so the English translation is novel. So it has this ranking in the text and this number of appearance. It appears 52 times in the text. Okay. As I was saying, so the two items of two of these 52 items of romance that appear in the text are indistinguishable, are identical each other. No, the text does not change if I exchange them. Now, consider the word storia, another word of the text. English translation is history, which has a lower energy level than romanzo. Why? Because it appears more times in the text. Now, suppose that we would ask Alessandro Manzoni to write a few additional paragraphs, okay, of this novel. Which word is more likely to appear? Romanzo or novel or history? History, right? Of course, you can also do this. Let's ask now a large language model like those of artificial intelligence to write a story about this. You will find history as more likely. This is the lack of statistical independence I was talking about. Yeah, because the idea is that the entire text carries meaning, an overall meaning of the text. And the words whose meaning is closer to the overall meaning of the text have a higher chance to appear if the text is continued to be written. How many minutes? Yeah, I can talk 10 minutes more. So I said at 5 o'clock, so we have, because otherwise I talk 35 minutes and not 45. Okay. So now the idea is then the more a word is used in a text, the more likely it is that the same word will appear in a new piece of text based on the previous one. But now let's use the terminology of physics. Now the terminology of physics makes sense. The more cognitons are in a given microstate, the more a new cogniton is likely to be in that microstate. But this expresses the typical tendency of bosons to clump together in the same microstates. The more bosons, the more photons, for example, are in a given microstate, the more a new photon is going to be in that microstate. So meaning plays apparently in this a fundamental role in the conceptual combination of the words of a text, because you have to preserve this kind of meaning coherence. Well, we think that the way in which meaning connects the concepts associated to the word of a text is very close to how quantum coherence, so the way in which meaning is organized, gives us an idea of how quantum entities are organized in physics, the type of organization of quantum entities in physics. About word randomization, the idea is the following. So I'll try to be short in this regard. So we have the original text, the one that you find in the digital library. Okay, so it contains n different words, small n, capital N, total number of words. So we found this web page, random.org, which allows to introduce this kind of randomness. You see that in the original text, we have n, capital N, placeholders, no? So you have the first word in the first placeholder, then another word in the second, and so on, right? So we have n capital letter placeholders. What this software does is, in each placeholder, you change randomly the word, the original word, by a random word chosen among the other n-1. Okay? So in this case, you are destroying the original meaning of the text because you are creating a random text. Okay? Now, it's more subtle in this. So you have a randomized text, T prime, that is produced. So what we found is that the quality of the fit of Bose-Einstein distribution is much worse, while Maxwell Boltzmann distribution starts to provide a good fit for the data. Then we said, why is it so? We calculated those parameters that you use in physics, no? The parameters A and B. Then what we discovered is that when we go from the original to the randomized text, the parameter B increases, drastically increases. You see, if you take the parameter B, where is the parameter B? There is a number counting the parameter B. I think it's this one. You see, it goes from -2 to 625, from -4 to 4,000. You see how drastically it increases. But what is B, the parameter B in physics? It is heat energy, because it's a parameter depending on the temperature. It is KT, where K is Boltzmann constant in physics. So the effect of randomization in a text plays a role that is very similar to an increase in the temperature in a gas. Because an increase in the temperature in a gas so determines its classical behavior. No? As temperature increases, you have more randomness that is introduced. The molecules start to behave in a statistically dependent way and so, independent way, and so on. So we have a perfect analogy with what occurs in physics. So we tried to provide, then I will stop. We tried to provide some kind of explanation for what we found, for the distribution we found, both in language and in physics. The way in which meaning is attributed in the combination of conceptual entities resembles formation of entanglement in the composition of physical entities. Because you have a phenomenon that we have called of contextual updating. You see, when you combine two words, so you are actually combining the two concepts, no, associated to those words, you have that the combination does not respect the rules of classical compositional semantics. This was well known even since the times of Eleanor Roche, right? Why? Because you have a new meaning, a new emergent meaning. Think of that, white lie. just as an example, you take white, you take lie, they have their own meaning. But when you put together, you have new emergent meaning that is created, that is not directly related to the original meaning. So this creation can be mathematically described as a phenomenon of entanglement. And indeed, we separately found that suitable combinations of two concepts violate Bell's inequalities, like it occurs in physics. Okay? There is more than this. In the writing process, the writer aims at making the piece of text as clear as possible, right? When you write a text, you try to make it as comprehensible as possible for the reader, right? Then this corresponds to a preparation process of a pure entangled state, right? So the idea is that when a text is written, the words of the text collaborate, organize because of meaning, to preserve meaning coherence. So to reduce the uncertainty of the text. And in particular, identical words tend to collapse in the same microstates. That's thus looking statistical independence. So it is this mechanism of meaning coherence, no? When you add the words, each time you add the word, you update meaning and so on, and you have to preserve meaning coherence that is responsible, in our hypothesis, of the occurrence of Bose-Einstein statistics in language. Okay, this idea that you try to preserve coherence in terms of meaning when you write a text. Okay, I'm coming to the end. Just a feedback into the foundations of quantum mechanics. In the early days of quantum mechanics, so I come back to Einstein times, the founding fathers did not attribute the appearance of Bose-Einstein statistics to physical indistinguishability. It was not physical indistinguishability that was at issue in the early days of quantum mechanics. They rather connected a statistical behavior that deviated from Maxwell Boltzmann statistics, for example, the behavior observed in a gas of photons, to the lack of statistical independence of microstates. Einstein wondered, so he was worried about this lack of statistical independence. He could not explain this lack of statistical independence in a gas of photons. And he wondered about the existence of a mysterious force that make the molecules or the photons attract each other in an ideal gas. With the advent of quantum mechanics, all this debate, scientific debate, who was a really high-level scientific debate, disappeared. Because the quantum mechanics arrived and the symmetry exchange postulate established by law complete indistinguishability, symmetry exchange, entanglement, and the lack of statistical independence. It was but it was a mathematical move, not a physically justified move, right? This was the idea. Well, coming back to this issue of statistical independence, we think that maybe there is some kind of coming back to Einstein idea. So the idea is that photons, because of entanglement through contextual updating, tend to clump or cluster together in the same microstate. The idea is that once I have a new photon in a gas of photons, this becomes automatically entangled with all the other photons that are already in the gas through mutual interactions, right? This would be the physical counterpart of the meaning coherence that you have to preserve in language. We are talking about different domains. Okay, it's just we are reasoning by analogies. But it might be a possible alternative explanation alternative to the symmetry exchange postulate. So the idea is that the formation of entanglement through contextual updating provides on the one side a more convincing physical justification for the appearance of, for example, Bose-Einstein statistics in physics, and partially support Einstein's idea of an attractive force linking identical photons in a gas. Of course, at that time, Einstein didn't know that this mysterious force was entanglement, right? We know this. But Einstein was right for one time that Einstein was right in quantum mechanics. Everybody says that he was wrong, no? Bell proved Einstein was wrong and so on. Now we are saying Einstein maybe was right in this respect. Okay, this is a list of publications and thank you very much for your attention. Please.